Every single day, we're surrounded by this hidden world. Inside our phones, our laptops, pretty much everything we plug in, there's a constant, super fast conversation happening. It's like a secret language that tames raw electricity and makes it useful. Today, we're going to learn a little bit of that language, and we'll start with the question you've probably asked yourself a bunch of times. Okay, so let's start with something we've all felt. You go to unplug your phone, and the charger itself is warm, right? Maybe even kind of hot. And that warmth, that's not a good thing. It's not a sign it's working hard. It's literally the ghost of wasted energy. And for a long, long time, that waste was just an accepted part of how electronics worked. So, to get why that happens, we got to look back at how we used to handle electricity. The old way was basically a brute force attack. Imagine trying to control a fire hose by just sticking your hand out to block some of the water. It's messy and it's not very smart. And this really breaks down the two big ideas. On the left, you've got the old way, the linear supply. It just takes all the extra voltage it doesn't need and burns it off as heat. Simple, yeah, but incredibly wasteful. But on the right, that's the modern way, the switching supply. It's so much smarter. Instead of burning energy, it's like a super fast chef, precisely chopping up the power and serving up exactly what the device needs. This is the big idea that let our gadgets get smaller and our batteries last for days instead of hours. So get this, that heat from an old charger, it's not a flaw, it's a feature. It's literally built into the design. The physics of it is right there. The power it wastes, the heat you feel, is just the voltage it needs to get rid of, times the current flowing. Wasting power isn't it failing, it's the only thing it knows how to do. But engineers looked at this and thought, there has got to be a better way, a much smarter way. Instead of just fighting the electricity, they figured out how to work with it. And this led to the invention of the switching converter, which was a total game changer. It's all about controlling power with timing and precision, instead of just brute force. And the whole process is actually beautiful in how simple it is. First up, an unbelievably fast switch chops the incoming voltage into these tiny, exact pulses. Then, a special kind of filter, one that uses parts that store and release energy instead of burning it, takes those choppy pulses and smooths them all out. And the result? A perfect, stable voltage. And you control the whole thing just by changing the timing of the switch. It's that elegant. And here is the magic number, the big payoff. In a perfect world, this method is 100% efficient. See, the parts, the switch, the inductor, the capacitor, they don't actually use the energy. They just borrow it for a split second and then give it back. They're just redirecting the flow like a masterful traffic cop. No waste, no heat, just pure, efficient power. Okay, but this super smart solution, it actually creates a brand new, kind of tricky puzzle. We can control our main switch, telling it exactly when to turn on and off. But what happens when another part of the circuit has a mind of its own and just refuses to listen? So let me introduce you to the diode. It's basically the most fundamental, uncontrolled switch out there. Think of it like a one-way valve or a one-way street for electricity. Current can go one way, but it absolutely cannot go the other way. You can't tell it what to do. The circuit conditions themselves decide when it turns on and off. And here's the trick to figuring out diodes. You don't focus on what they do, you focus on what they absolutely positively cannot do. There are just two hard rules. A diode cannot have a positive voltage across it without just turning on, and it can't have current flowing backward through it. That's it. Those two cannots are the key to predicting everything it does. So this is a huge problem, right? If you're designing something, how on earth are you supposed to predict how it will work if you don't even know if your one-way valves are open or closed at any given moment? It seems like it would be impossible to figure out. Well, to solve this exact problem, engineers have this kind of secret toolkit. It's really just two powerful ways of thinking that let them solve the puzzle by basically being a detective and listening for the circuit's natural rhythm. All right, tool number one is something called the method of assumed states. And honestly, it's less about complex math and way more about being a good detective. Here's the game plan. First, you just make a guess. You assume the diode is on, for example. Then you analyze that new, much simpler circuit. And here's the crucial part. You check your answer. Did your result break one of the diode's rules? Like, did you calculate a backward current for a diode you said was on? Well, that's impossible. So if a rule was broken, you know your first guess was wrong. You just go back, make the opposite guess, and try again until everything makes sense. Okay, so that's our first tool. The second one is all about understanding the circuit's natural rhythm. It's called periodic steady state.
Think about it, when you first flick a switch on a device, everything's a little chaotic for a split second, right? That's called the transient state. But after a moment, it settles down. It finds its groove. It enters this periodic steady state where every single on-off cycle is a perfect, predictable carbon copy of the one that came before it.
And that rhythm, that predictability, it gives us a total superpower when we're analyzing these things because we know that over one full repeating cycle, the energy in certain components has to end up right back where it started. That means for a key part called an inductor, the average voltage across it has to be zero. And that one little rule, that changes everything. And this isn't just some weird abstract rule, by the way. This is the exact reason those filters we talked about actually work. The fact that the average voltage must be zero is what forces the circuit to behave in a smooth, predictable way. It's not magic, it's just the fundamental physics of the system doing its thing. So let's see this whole toolkit in action. Let's put it to work. Our goal is to take messy AC power from the wall and make it smooth DC. Our first guess is to just add an inductor to filter it. But wait, our PSS rule tells us that won't work. The inductor's physics will actually force the output to average out to zero, which is totally useless. Our detective work tells us our first idea is flawed. So we arrive at the solution. We add a second diode. And boom, this brilliant little addition creates a clean, positive-only wave that the inductor can easily smooth out. It's the perfect solution, and we only found it by using our tools. And you can see the payoff right here on this chart. The unfiltered output is just a bumpy mess. Our first attempt at filtering was even worse. It made the average DC voltage zero, totally useless. But the correctly filtered circuit, the one we designed with our toolkit, gives us exactly what we wanted all along, a nice, smooth, stable DC output. And I really want to stress, this is not just a theoretical exercise for a class. This exact two-diode design is a fundamental building block of modern electronics. It's humming away quietly inside millions, probably billions of devices you use every single day, all because some clever engineers knew how to speak this secret language. So the next time you plug in your phone and feel that little bit of warmth, you'll know what's really going on inside. It's not brute force. It's an elegant, high-speed dance of switches and states. And now that you know a bit of the language, you can start to see the incredible, invisible engineering that powers our world. It makes you wonder, right? What other secrets are hiding in plain sight?